These glowing cosmic sculptures are not what they seem. Planetary nebulae, the beautiful final shrouds of sun-like stars, hold secrets that defy our textbooks. By the end of this journey, you will see stellar death in a completely new light. We will uncover why their perfect shapes are an illusion, how binary stars perform a gravitational dance of creation, and what bizarre chemical factories they truly are. This is a countdown of 50 strange discoveries, each one peeling back a layer of cosmic mystery. What do you believe is the greatest wonder a dying star can leave behind? The journey of understanding begins with a simple mistake. Our first strange discovery is not about a nebula's structure, but its very name. When the astronomer William Herschel peered through his telescope in the 1780s, he saw small, rounded, glowing disks. They reminded him of the newly discovered planet Uranus, a greenish-blue orb in his lens. So he called them planetary nebulae, thinking they were perhaps collections of new worlds or stars shrouded in gas. It was an honest, logical error for the time, but this single label created a cosmic misnomer that has lasted for centuries. These objects have absolutely nothing to do with planets. They are the final, fleeting breaths of dying stars. That initial confusion is profoundly telling. It set the stage for every surprise to come because it shows us that the universe often presents itself in disguise. What we see is rarely the full story. The name Planetary Nebula is a fossil, a permanent reminder in our star charts of how human knowledge grows. We look, we interpret based on what we know, and sometimes we get it beautifully wrong. That legacy of misinterpretation makes the truths we've since uncovered all the more astonishing. Herschel's naming error was only the first layer of illusion. For decades after his discovery, the assumption persisted that these were simple, round objects. A dying star was a sphere, so its expelled shroud must be a sphere as well. It seemed like cosmic logic, but as telescopes grew more powerful, that comforting symmetry began to crumble. The second strange discovery shattered the myth of the perfect shell. Planetary nebulae are almost never spherical. Instead, they are cosmic artists of asymmetry, forming intricate, often breathtakingly lopsided shapes. Some stretch into elegant hourglasses or two-lobed structures we call bipolar. Others appear as elongated ovals or even stranger, as multipolar formations with multiple axes of symmetry, like a celestial cloverleaf. One of the earliest and most famous examples is the Dumbbell Nebula. Even through a modest telescope, it doesn't look like a planet or a simple bubble. It looks like a glowing weightlifter's dumbbell, a clear double-lobed structure with a pinched waist. This was a visual clue that something powerful and directional was at work, a force that could take a star's final, spherical breath and sculpt it into something so deliberately shaped. That observation posed the central mystery that would drive astronomers for generations. If a star dies as a symmetrical ball of gas, what invisible hand molds its funeral shroud into butterflies, eyes, and intricate rings? The answer could not be found in the nebula's glowing gas itself, but in the silent, dark environment surrounding the dying star. The quest to understand these asymmetric shapes led astronomers to peer deeper into the nebula tapestry, where they found not just structure but strange, high-speed projectiles. The third discovery unveiled objects so bizarre they earned the acronym FLIRES for Fast Low Ionization Emission Regions. These are not gentle clouds. They are small, incredibly dense knots of gas fired out from the central star like cosmic bullets. Often they appear in pairs, two symmetrical blobs positioned perfectly along the nebula's polar axis, far ahead of the expanding main shell. Their speed is staggering, sometimes hurtling through space at hundreds of kilometers per second, much faster than the nebula's general expansion. But their strangeness doesn't end with their velocity. Their chemical signature is all wrong. While the main body of a planetary nebula glows with highly ionized gas, atoms stripped of many electrons, FLIRES are regions of low ionization. This means the atoms there are more neutral, holding onto their electrons more tightly. It is as if, within the same stellar funeral, two completely different kinds of material were ejected under two different sets of rules. So what could possibly launch these dense, fast, and chemically distinct bullets? The leading theory points back to the hidden choreography of a binary star system. Astronomers suspect flyers are the product of powerful jets. Imagine the dying star's companion, a smaller star or even a dense white dwarf, pulling material from its expanding partner. This stolen gas forms a swirling, super-hot disk of matter called an accretion disk. From the poles of this disk, like focused cosmic blowtorches, narrow jets of material can erupt. These jets, channeled and accelerated by intense magnetic fields, could punch through the slower-moving ejected shroud, carrying with them a different blend of chemistry from deeper within the stellar system. Flyers, then, may be the permanent scars left by these violent, directed outbursts, a fossil record of a gravitational struggle happening in the heart of the chaos. They are a stark reminder that the death of a star is not a quiet, uniform fade, but a dynamic and often violent series of events. If jets from a binary companion can carve out structures, what force guides and confines the material itself? This brings us to our fourth strange discovery, a hidden force that may be the master architect behind the nebula's final form. For a long time, astronomers believed magnetic fields were a feature of a star's vibrant youth, not its quiet death. In the final, chaotic act of a planetary nebula's creation, simple thermal pressure and stellar winds were thought to be the dominant shapers, but that assumption has been overturned. We now see compelling evidence that powerful, organized magnetic fields emerge from the dying star's core, acting as an invisible lattice that sculpts the outflowing gas. The clues come from starlight itself, specifically its polarization. As light travels through space filled with elongated dust grains, those grains can align themselves like tiny compass needles in the presence of a magnetic field. This alignment polarizes the light, twisting it in a specific direction that our telescopes can detect. Observations of many planetary nebulae reveal this exact signature. The dust surrounding the central star is not scattered randomly. It is lined up, pointing in coherent patterns that trace the lines of a powerful magnetic field. Think of it like iron filings around a bar magnet. The filings arrange themselves along the magnetic field lines, revealing a structure you cannot see with your eyes alone. In a planetary nebula, those field lines act as a conduit and a constraint. They funnel the star's expelled material, channeling it into jets and preventing it from expanding in all directions equally. This could be the fundamental answer to the mystery of asymmetry. A perfectly spherical star does not die into a perfect sphere because its final breath is threaded through a magnetic skeleton. The field gives direction and form to the chaos, explaining why we see delicate bipolar lobes, narrow wastes, and even the intricate, knotty textures within the glowing gas. It is a revelation that redefines the final chapter of a star's life. The death of a sun-like star is not a passive dissipation. It is an active, magnetically choreographed performance where invisible forces write their signature in light and gas for all the universe to see. This magnetic lattice often has a partner in cosmic crime. The fifth strange discovery reveals that the beautiful chaos of a planetary nebula is rarely a solo act. Astronomers now suspect a majority, perhaps even most, of the central stars lighting up these nebulae are not single, but part of binary or multiple star systems. That second star is the hidden sculptor, its gravity the chisel that carves the intricate shapes we see. In a solitary star's death, the expelled envelope might puff away in a roughly spherical shell. But introduce a companion and everything changes. The two stars engage in a gravitational dance, and as the dying star swells, its outer layers can be pulled toward its partner. This stolen material doesn't just vanish, it spirals around the companion, forming a superheated, spinning disk of gas. From this accretion disk, the physics becomes an artist's toolkit. The disk can focus and launch those powerful bipolar jets we discussed earlier, which punch through the slower material. Simultaneously, the orbital motion of the two stars acts like a giant egg beater in the center of the ejected cloud, funneling and shaping the outflow into two distinct lobes. The result is the precise bipolar or hourglass structure so common among these objects. A stunning example is the Cat's Eye Nebula, one of the most complex planetary nebulae known. Its Hubble images show a breathtaking series of concentric gas shells, jets, and knots, all radiating from a brilliant central point. For years, its intricate structure seemed almost impossibly elaborate. The leading explanation, a binary star system at its heart. The suspected companion star's gravity could have periodically stripped material from the primary star in pulses, creating those concentric rings, while also channeling other outflows into the dramatic, bubble-like lobes and high-speed jets visible in the image. The Cat's Eye is not a serene farewell, it is a gravitational fingerprint, a fossilized record of a stellar partnership that transformed a simple death throw into a Baroque masterpiece. This realization shifts our entire perspective. When we gaze at these glowing nebulae, we are not looking at the death of one star. We are witnessing the final, transformative chapter in the life of a stellar relationship, where gravity writes its last poem in light and gas. But what happens in the moments just before the final, glowing nebula emerges? The answer lies in a fleeting and violent transitional phase, a cosmic tantrum caught in the act. Our sixth discovery peers into this brief window, focusing on a bizarre class of objects known as water fountain stars. These are not yet full planetary nebulae, but their immediate precursors caught in the act of violent transformation. They are called water fountains not because they spray liquid water, but because they emit powerful, focused beams of water vapor. More specifically, they produce what astronomers call a maser. A maser is like a cosmic laser, but for microwave radiation instead of visible light. In the dense, shocked gas around these dying stars, water molecules become excited and emit a tremendously bright, coherent signal at a specific microwave frequency. It is a natural amplifier in space, and its intensity tells us something extraordinary is happening. These water masers are not gently drifting away. They are detected racing outward at astonishing speeds, often hundreds of kilometers per second, in tightly collimated jets. This tells us we are witnessing an eruption. The star has begun its final, intense episode of mass loss, but the process is not yet stable or symmetrical. It is a focused, high-velocity outburst, likely channeled by the magnetic fields and accretion disks of a binary companion, just as we saw in full planetary nebulae. The water fountain phase is incredibly short-lived, perhaps lasting only a century or two, a blink in cosmic time. This makes these objects rare and precious laboratories. They offer us a live, real-time view of the violent shaping forces at work, a snapshot of the moment when the invisible sculptors, jets, magnetic fields, and binary companions are actively carving the raw material that will soon be lit up by the exposed stellar core. By studying water fountain stars, we are essentially watching the birth pangs of a planetary nebula, witnessing the chaotic moment when a star's death throw is given its definitive, asymmetric form. These violent birth pangs leave behind a beautiful, glowing structure, but when astronomers began to carefully weigh that final product, they ran into a baffling accounting error. Our seventh discovery reveals the missing mass problem. The math simply does not add up. A typical Sun-like star during its final red giant phase is known to shed a tremendous amount of material, roughly half its entire mass. That is a colossal amount of gas and dust, enough to form thousands of planets. Yet when we measure the total mass of the bright, iconic planetary nebula that results, we find only a small fraction of that expelled material. It is as if a baker used 10 pounds of flour but only produced a 1-pound loaf of bread. So where did the rest of the ingredients go? This is not a trivial accounting glitch. It strikes at the heart of our understanding of stellar life cycles. One compelling theory suggests the missing mass is not truly gone but hiding in plain sight. Before the star's core becomes hot enough to ionize and light up the expelled gas, that material drifts away for thousands of years, forming a vast, cold, and invisible halo around the central star. When the ultraviolet flash finally arrives, it only energizes the innermost, densest parts of this halo, creating the brilliant nebula we see. The rest of the gargantuan, tenuous outer shell remains dark and faint, detectable only with the most sensitive radio telescopes hunting for specific molecular signatures. Another possibility is that a significant portion of the mass was lost in a different form, much earlier in the star's death process. Perhaps powerful, fast winds during the red giant phase carried away material at such high speeds that it simply dissipated into the interstellar medium long before the iconic nebula formed. Or maybe binary interactions, those hidden sculptors, flung huge amounts of mass out of the system entirely on trajectories we cannot easily trace. This missing mass mystery matters because it changes the entire story of a star's final contribution to the galaxy. The recycled elements, the carbon, nitrogen, and oxygen forged in its heart, are the building blocks for new stars, planets, and life. If we are underestimating how much material a dying star actually returns to space, we are misunderstanding the cosmic cycle of life and death itself. The beautiful glowing nebula, then, is just the brilliant tip of a much larger, darker, and more massive iceberg. That missing mass is propelled outward by a force of staggering violence. The eighth discovery reveals these beautiful shrouds are not drifting placidly into space. They are exploding outward at supersonic speeds. The shells of gas expand at velocities between 20 and 50 kilometers per second. To grasp that scale, consider a jet fighter breaking the sound barrier at just over 1 kilometer per second. The material in a planetary nebula is moving dozens of times faster, a supersonic shockwave of stellar debris. Astronomers measure this breathtaking expansion using the Doppler shift, the same principle that changes the pitch of a passing ambulance siren. As the nebula expands, one side of its shell moves toward us, squeezing its light waves and shifting them slightly toward the blue end of the spectrum. The opposite side moves away, stretching its light toward the red. By carefully splitting the light from different parts of the nebula into a spectrum, scientists can measure this red and blue shift, calculating the precise speed of the outward rush. But this measurement leads to a deeper question. What engine could possibly accelerate billions of tons of gas to such phenomenal speeds? The answer lies in a sequence of powerful events within the dying star's core. After the star sheds its outer layers, the hot, exposed core, now a white dwarf, begins to blast the surrounding cloud with an intense wind of charged particles. This fast wind, traveling at thousands of kilometers per second, slams into the slower-moving material ejected earlier. It is like a cosmic snowplow hitting a drift, creating a powerful shockwave that heats and compresses the gas, accelerating it to the supersonic speeds we observe. The energy required for this is immense, drawn from the final, furious contraction and heating of the stellar core. The serene glow of a planetary nebula, therefore, masks a scene of continuous high-energy collision. It is a supersonic sculpture, its form constantly being reshaped by the relentless push from within. That supersonic expansion is powered by a stellar engine of unimaginable heat. The ninth strange discovery confronts us with a temperature paradox so extreme it defies everyday intuition. The tiny white dwarf star at the heart of a planetary nebula is one of the hottest objects in the entire universe. While its surface once simmered at a few thousand Kelvin as a bloated red giant, that same stellar core, now exposed, can skyrocket to over 100,000 Kelvin. To grasp that number, our Sun's surface is a relatively cool 5,800 Kelvin. These central stars are 20 times hotter. They are so ferociously hot that they emit the majority of their energy not as visible light, but as blistering ultraviolet radiation, light our eyes cannot see but which carries tremendous power. This radical transformation happens with startling speed. Once the star sheds its insulating outer layers, there is nothing left to hold up the incredibly dense core. It is a sphere of degenerate matter, mostly carbon and oxygen, about the size of Earth but containing nearly the mass of our Sun. Under its own immense gravity, this core contracts further, and as it squeezes down, it heats up dramatically. Think of a bicycle pump. When you compress the air inside, the pump's barrel gets warm. On a cosmic scale, the contraction of an entire stellar core unleashes a phenomenal wave of heat, concentrated onto a surface no larger than a planet. This is the ultimate cosmic furnace, and its ultraviolet output is the secret behind the nebula's famous glow. The beautiful colors of a planetary nebula are not emitted by the gas itself. They are a fluorescent response. When those intense UV photons from the central star slam into the atoms in the expanding shell, they rip electrons away, ionizing the gas. When the electrons eventually recombine with the atoms, they release energy as light at specific, beautiful colors. The iconic red glow of hydrogen, the blue-green of oxygen, the subtle hues of nitrogen. This is all starlight reprocessed by a cosmic cloud. The nebula is a magnificent fluorescent sign, lit by a pinpoint of unimaginable heat. This means the breathtaking spectacle we admire is not the fire of the star, but its echo, a final, radiant scream of ultraviolet energy translated into visible color. The central star, small and searingly blue-white to our instruments, is the invisible artist painting with an ultraviolet brush on a canvas of its own remains. That ultraviolet brush paints with a palette forged in stellar furnaces. Our 10th discovery reveals planetary nebulae are not just glowing shrouds, they are cosmic chemical factories, and their products are often bizarrely lopsided. When astronomers analyze the light from these objects, splitting it into detailed spectra, they find unexpected overabundances of specific elements. Carbon, nitrogen, and oxygen shine brighter than they should, their spectral signatures screaming from the gas. This is a direct fingerprint of the star's death process. During its final, turbulent phases, deep convection currents like a boiling pot reaching its bottom dredge up material from the star's interior. This material has been freshly cooked by nuclear fusion, transforming hydrogen into helium and helium into heavier elements like carbon and oxygen. These newly forged atoms are then carried to the surface by powerful stellar winds and ejected into space, enriching the nebula. The result is a shell of gas that is chemically distinct from the star's original composition, a snapshot of its final nuclear reactions, but the strangeness goes deeper. Some planetary nebulae show traces of even rarer elements like barium or technetium, known as S-process elements. The S stands for slow because these heavy atoms are built slowly, one neutron at a time, in the intense, high-density environment deep within a red giant star. Finding them in the nebula means these heavy elements, forged in the star's final days, were also violently churned to the surface and launched into the void. This chemical bounty is the star's ultimate legacy. Every atom of carbon in your body, every breath of oxygen you take, was once forged in a star and likely scattered by an event just like this. A planetary nebula is the delivery mechanism, the beautiful, glowing truck that carries these essential ingredients for planets and life across the galaxy. That chemical legacy is not always spread evenly. In the vast, eye-like expanse of the Helix Nebula, we find a haunting and beautiful structure that defies simple explanation. This 11th discovery focuses on thousands of ghostly tadpoles swimming in the deep. They are called cometary knots, and they fill the inner rim of the helix like a school of cosmic fish, each one a dense knot of gas and dust with a bright, streaming tail. The scale is staggering. Each knot's head is roughly twice the size of our entire solar system, yet they appear as tiny, delicate wisps against the nebula's grand scale. Their tails, glowing with ionized gas, all point directly away from the nebula's central, dying star, like flowers turning toward the sun or iron filings aligning to a magnet. This radial alignment is the first clue to their bizarre nature. They are not randomly scattered debris, but objects shaped by a powerful, directional force emanating from the center. For decades, their origin was a profound puzzle. How could a roughly spherical shell of gas break apart into so many identical, self-contained structures? The leading theory is as elegant as it is violent, involving a cosmic interplay of light and shadow. Imagine the central white dwarf as an ultraviolet lighthouse, its intense radiation relentlessly eroding the expanding shell of gas from the inside out. But the shell is not perfectly smooth. It contains denser, colder clumps of material, likely formed as the ejected gas cooled and fragmented. These clumps act like umbrellas. They cast long, protective shadows of neutral gas behind them, shielding the material in their wake from the star's blistering radiation. The result is a sculpting process. The unprotected gas around the clump gets ionized and blown away by the stellar wind, leaving only the dense head and its long, shadowed tail intact. Over time, the pressure from the radiation and wind even shapes that tail, compressing it and causing it to glow brightly, pointing directly away from the destructive source. So each cometary knot is not an object that was ejected in this shape. It is a survivor, a dense remnant being slowly evaporated and sculpted by the very light that makes the nebula visible. They are transient monuments destined to eventually dissipate entirely, leaving behind only their enriched contents to drift into the galactic void. The Helix Nebula's eerie gaze is, in truth, filled with the shadows of its own destruction. The shadows in the helix are not the only way light sculpts these nebulae. Sometimes the star itself becomes a strobe light, and its flashes paint history onto the surrounding darkness. This is the 12th strange discovery, revealed in the haunting beauty of the Egg Nebula, a protoplanetary nebula still in its formative stage. At its heart is a dying star hidden by a thick, dark waste of dust, but from its poles, 4 brilliant searchlight beams pierce the gloom, illuminating vast, concentric shells of material far from the center. These are not solid structures, but light echoes, one of the most elegant tricks of perception in the cosmos. Here is how it works. The central star is not shining steadily. It is undergoing violent pulsations, sending out intense, brief flashes of light into space. When one of these flashes reaches a distant, previously invisible shell of dust ejected by the star thousands of years earlier, it lights it up. We see that shell suddenly glow, but light takes time to travel. The flash that illuminated the outermost shell we see today actually left the star centuries before the flash that lit up an inner shell. Because we see all this light arriving at our telescopes at the same moment, we are witnessing multiple chapters of the star's history simultaneously. It is like hearing an echo in a canyon, where each returning sound represents a shout made at a different time. The Egg Nebula's nested rings are a cosmic timeline, a series of fossilized pulses of mass loss, each flashbulb moment frozen in an expanding sphere of dust. By measuring the angular size of each ring and knowing the speed of light, astronomers can perform a breathtaking calculation. They can map the three-dimensional structure of the dust and determine exactly when, in the star's past, each great heave of material was expelled. This transforms the nebula from a static picture into a living biography. We are not just looking at a dying star, we are watching a recorded playback of its final millennia, each concentric shell a page in its diary written in reflected light. This strobe light effect allows us to dissect the death throes of a star with a precision otherwise impossible, revealing that the final act is not one smooth exhalation, but a series of fitful, powerful breaths. That strobing light show in the Egg Nebula reveals a history of violent ejections, but what happens when that expelled gas flies into an almost perfect void? The answer is found in a ghostly bow tie in the southern sky, holding a record of cosmic cold. The Boomerang Nebula is officially the coldest known natural place in the entire universe. Its temperature hovers at a mere 1 degree above absolute zero, that theoretical point where all molecular motion stops. It is even colder than the faint, uniform glow of the Big Bang itself, which permeates all of space at nearly 3 Kelvin. This nebula is a cosmic deep freeze, and its chill is a direct result of its own violent birth. The mechanism is a classic physics phenomenon called adiabatic cooling. Imagine using a spray can. When you press the nozzle, the compressed gas inside expands rapidly as it escapes into the open air. That expansion requires energy, which the gas takes from its own internal heat, causing the can to feel cold to the touch. The Boomerang Nebula is a cosmic version of this on a staggering scale. Its central star is ejecting material at a phenomenal speed, over 150 kilometers per second. But crucially, this gas is expanding into a region of space that is remarkably empty, a near-perfect vacuum. With almost nothing around to resist it or transfer heat, the gas can expand at an incredible rate. As it does, the individual atoms and molecules must spread out over a vast volume, and the energy of their motion is diluted across that immense space. They literally cool themselves by their own frantic expansion. This is not a gentle cooling. It is a runaway thermodynamic event, plunging the nebula's material to a temperature that defies the ambient warmth of the universe. Studying this frigid object is more than just record-keeping. It is a unique laboratory for understanding the fundamental behavior of matter and gas dynamics under the most extreme conditions. We can observe how molecules form and behave in this profound cold, testing our models of physics against a natural experiment no human lab could ever replicate. The Boomerang Nebula shows us that the death of a star is not just about heat and light. It can also create, through sheer explosive violence and emptiness, the ultimate cold. A cosmic bow tie floats in the southern sky, but its center holds a deeper mystery than mere cold. Our 14th discovery confronts us with a ghost that has seemingly vanished. In a handful of planetary nebulae, the central star, the brilliant engine that should be lighting up the entire structure, is simply not there. The most famous example is a beautiful ring nebula named SU-WT2. Through a telescope, it appears as a perfect, glowing annulus of gas, a celestial wedding band adrift in the black. But at its heart, where a searingly hot white dwarf should blaze, there is only darkness. It is as if you found a brilliantly lit lantern in a field, but no flame inside to explain the light. This presents a profound cosmic puzzle. The very definition of a planetary nebula requires an ultraviolet source to excite the gas. So what is powering the glow of SU-WT2? Astronomers have proposed several eerie possibilities, each stranger than the last. The first is a story of rapid cosmic fading. Perhaps the central star did exist, but it cooled and dimmed at an astonishing rate, transitioning from a blazing ultraviolet source to a faint, cold ember in a geological instant. This would be like a light bulb filament burning out the moment you flip the switch, leaving only the afterglow in the surrounding lampshade. While possible, this requires a very specific and rare stellar evolution path. The second and more compelling theory returns to the hidden hand of binary stars. Imagine the central source is not one star, but two, locked in an incredibly tight, fast orbit. If we are viewing the system edge-on, the stars might eclipse each other regularly, their combined light appearing as a single, faint and flickering point lost in the nebula's glow. Or the binary interaction could have been so violent that it ejected the nebula in a single, catastrophic event, leaving behind a pair of stars that are now too cool or too distant from each other to produce the intense radiation we expect. There is even a third, more speculative idea that the nebula itself is a cosmic impostor. Perhaps it was not formed by a dying sun-like star at all, but by a different, rarer event like the merger of two white dwarfs, which could produce a ring of gas without leaving behind a traditional central engine. The empty heart of SU-WT2 is a silent challenge to our textbooks, a reminder that for every rule we write about the universe, nature enjoys crafting a beautiful, glowing exception. Sometimes a stellar death is not the final act. Our 15th discovery reveals a star can be resurrected in a spectacular cosmic encore known as the born-again phenomenon. This is not a metaphor. It is a violent, real event where a white dwarf, the cooling ember of a star's core, suddenly reignites nuclear fusion on its surface. The process begins deep within the star's final moments. As a dying star sheds its outer layers to become a white dwarf, it can leave behind a thin, unstable shell of unburned helium just above its carbon-oxygen core. If conditions are right, this helium shell can suddenly ignite in a final, furious flash of fusion. The energy released is catastrophic. It causes the entire white dwarf to balloon back out, re-inflating to a red giant size in a matter of mere decades. The star is literally born again, returning to a phase it left thousands of years earlier. But this second life is brief and explosive. The reborn giant experiences powerful new stellar winds that blow off its freshly expanded outer layers, ejecting a second, much younger nebula. The result is a cosmic nesting doll, a faint, old, expanding planetary nebula from the star's first death, and inside it, a new, dense, fast-moving shell of gas from its dramatic rebirth. One of the most dramatic examples is Sakurai's object. In the 1990s, astronomers watched in real time as a faint star in the constellation Sagittarius, thought to be a settled white dwarf, violently erupted in brightness. Within a few years, it transformed into a cool giant, shrouded itself in dust, and began ejecting a new nebula. We are witnessing a born-again event as it happens, a stellar Lazarus rising from its own ashes. This process may also explain the breathtaking complexity of nebulae like the Eskimo Nebula. Its iconic structure shows a bright, inner bipolar bubble surrounded by a fainter, more spherical halo of filamentary gas. This could be the signature of a two-act drama, an initial spherical mass loss followed by a later, born-again outburst that was sculpted by binary interaction or magnetic fields into the intricate inner form we see today. A born-again star forces us to rewrite the final chapter. Stellar death is not always a linear path to darkness. It can include a final, brilliant, and violent footnote where the corpse itself briefly returns to life, adding one last, complicated layer to its own funeral shroud. A star's final act should be a private affair shaped by its own unique history. Yet when astronomers step back to look at the grand tapestry, they see a pattern that suggests a larger hand at work. Discovery 16 reveals a peculiar cosmic conformity. The orientations of bipolar planetary nebulae are not random. Their long axes, the direction of their magnificent lobes, show a surprising tendency to align with the plane of our Milky Way galaxy. This is deeply strange. We have spent this journey learning how a star's death is sculpted by intimate, local forces: the spin of the star, the gravitational pull of a binary companion, the star's own magnetic field. These are personal details, like the unique wrinkles on a face. So why would these intensely personal structures, scattered across thousands of light years, all point in a direction that references the entire galaxy? It is as if billions of people living independent lives all decided to face the same direction when they took their final breath. This alignment is a subtle statistical trend, not a perfect rule, but it is strong enough to be undeniable. When researchers mapped the orientations of over 100 bipolar nebulae, they found their lobes were more likely to be parallel to the galactic plane than perpendicular to it. The implication is staggering. Something about the galaxy itself, its vast, diffuse environment, is whispering a direction to dying stars, influencing the very axis of their explosion. This points to forces operating on a scale far beyond any single stellar system, forces that can nudge a cataclysm. Two leading theories attempt to explain this galactic guidance. The first invokes the Milky Way's incredibly weak but pervasive magnetic field. These field lines run along the plane of the galaxy, a ghostly grid stretching for tens of thousands of light years. As a star dies and its envelope begins to expand, this tenuous magnetic field could act like a set of invisible railway tracks, gently channeling the outflowing material to align with it over immense distances. The second theory looks to gravity, not of a companion, but of the galaxy as a whole. The collective gravitational pull of all the stars, gas, and dark matter in the galactic disk creates a tidal force, a stretching effect. This force could subtly influence the orientation of the star-forming cloud the star was born from eons ago, or perhaps even affect the angular momentum of the dying star's system itself, predisposing its spin axis to lie in the galactic plane. Either way, the message is profound. No star dies in true isolation. Its final, most beautiful act is a collaboration between its own fiery heart and the silent, galaxy-wide architecture in which it has lived its entire life. That galactic whisper can sometimes produce a shape of startling geometry. In the constellation Monoceros, a dying star system has crafted not soft lobes or ethereal rings, but a structure that looks like a celestial red jewel set in a frame of perfect X's. This is the red rectangle nebula, and its true strangeness is not just in its shape, but in the very color of its light. Discovery 17 confronts us with a spectrum that defies explanation. When astronomers split the nebula's crimson glow into its constituent colors, they find something utterly bizarre. Instead of the smooth, broad emission lines typical of glowing gas, the red rectangle's spectrum is dominated by a series of sharp, equally spaced bands of light in the red part of the spectrum. This phenomenon is called the extended red emission, or ERE, and its origin remains one of the great unsolved puzzles in nebula physics. Normal nebula glow comes from atoms. An electron is knocked loose and then falls back, releasing a photon of a very specific color. The ERE is different. It is a broad, featureless hum with these strange, sharp spikes superimposed on it. This signature points not to atoms, but to something more complex, dust. Specifically, it suggests that tiny grains of dust in the nebula are absorbing ultraviolet light from the central star and re-emitting it as this mysterious red luminescence. But what kind of dust does this? Common interstellar grains of silicate or carbon soot do not produce this effect. The leading suspect is a class of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAHs. These are flat, chicken wire-like molecules made of carbon and hydrogen, essentially tiny flakes of soot. They are known to fluoresce under ultraviolet light. However, even PAHs do not perfectly match the sharp, spiky bands of the red rectangle. This has led to other, more exotic proposals. Could the dust be made of entirely new forms of carbon, like tiny diamonds, or onion-like fullerenes forged in the stellar outflow? Or perhaps the red emission comes from silicon nanoparticles, tiny specks of stardust that luminesce in a unique way. The red rectangle is a cosmic chemistry lab, producing a type of dust or molecule we have not yet fully identified on Earth. Its striking X-shaped bipolar structure, likely carved by a dense disk of dust around a close binary star system, provides the perfect, sheltered environment for these complex materials to form and shine. This nebula challenges the very models of how dust condenses and behaves in space. It tells us that the final breaths of stars are not just recycling simple elements, but can be factories for intricate, luminous chemistry we are only beginning to comprehend. The red rectangle's strange chemistry emerges from a sheltered disk, but what shapes the death of a star spinning alone? Our 18th discovery reveals that even a solitary star can sculpt an asymmetric farewell if it possesses a powerful secret, rapid rotation. We have focused on binary companions as the master sculptors, but a single, fast-spinning star holds its own chisel. As a star like our Sun ages and expands into a red giant, its rotation can dramatically speed up, a consequence of the same physics that makes a spinning ice skater pull in their arms to whirl faster. This increasing spin flattens the star, creating a noticeable equatorial bulge. Gravity is weaker at this bulging equator, and the star's atmosphere becomes more tenuous there. This sets the stage for a lopsided death. In some models, enhanced mass loss can occur right at this weakened equator, shedding material in a dense, dusty ring that constricts the later outflow, leading to a bipolar shape. In other scenarios, the rapid rotation coupled with the star's own magnetic field can funnel winds preferentially from the poles, creating fast, focused outflows even without a companion star. The result is a spectrum of forms, from pinched wastes to subtle elongations, all authored by spin alone. But rotation's influence may start even earlier with a phenomenon poetically called photospheric whispering. Imagine the roiling surface of a red giant as a vast, stormy ocean. Within this churning plasma, powerful sound waves, actually pressure waves, ripple through the star's outer layers. These are not sounds we could hear, but rhythmic oscillations of incredible power. As they travel outward, they can amplify, becoming supersonic shocks that literally punch material free from the star's gravitational grip. This is a line-driven instability where the very light pushing on atoms in the atmosphere creates a feedback loop of acceleration. The whispers become shouts, triggering localized, clumpy eruptions of mass loss. This process does not eject a smooth, uniform shell. It puffs out material in fits and starts like a candle sputtering in the wind, creating the intricate filaments and knotty structures we see within many nebulae. So a dying star's final form is a conversation between many voices, the shout of its ultraviolet core, the gravitational pull of a hidden companion, the silent guidance of galactic magnetic fields, and the inner whisper of its own spinning, pulsating heart. Each nebula is the unique record of that conversation, a fossilized moment of stellar sound and fury. The whispers of stellar chemistry sometimes assemble into structures of startling perfection. Discovery 19 unveils a cosmic architect building microscopic soccer balls in the void. Within the light of certain planetary nebulae, astronomers found the unmistakable fingerprint of fullerenes, the magnificent carbon cages known as buckyballs. These are not simple soot or graphite. A C60 fullerene is a hollow sphere of 60 carbon atoms arranged in a perfect lattice of hexagons and pentagons, a geometry identical to a classic soccer ball. Its larger cousin, C70, resembles a tiny, elongated rugby ball. For years, these molecules were a laboratory curiosity, a triumph of human nanotechnology. Then, their spectral signatures, specific patterns of infrared light absorbed by their unique bonds, were spotted shining from the dusty envelopes of dying stars. This was a definitive detection. The furnaces of planetary nebulae were not just making atoms, they were assembling those atoms into intricate, stable cages. The significance of this discovery cannot be overstated. It means the violent, chaotic environment of a stellar death is also a precision workshop for complex organic chemistry. The process likely begins with the star's own carbon, forged in its final nuclear fires and ejected into space. In the expanding, cooling shell, these carbon atoms link together into chains and rings. Under the right conditions of temperature and density, these precursors can curl in on themselves and stitch together into these resilient, geodesic spheres. Buckyballs are incredibly tough. They can withstand intense radiation and harsh conditions, making them perfect interstellar travelers. Finding them in planetary nebulae suggests these objects are prolific producers of such molecules, casting them out into the galaxy by the trillions. Each nebula becomes a seed pod, scattering not just raw elements, but pre-assembled, complex organic structures into the interstellar medium. These carbon cages could later drift into nascent stellar systems, perhaps clinging to dust grains in protoplanetary disks. They may act as protective carriers for other molecules, or even as catalysts for further chemical reactions on young, rocky worlds. The discovery ties the death of one star directly to the potential for life around another. Those beautiful, glowing shrouds are not merely tombs. They are cosmic nurseries for the most intricate chemistry, factories assembling the very frameworks upon which the building blocks of biology might one day form. The soccer ball cages of carbon drift from cooler nebulae, but some stellar deaths are forged in a far more violent furnace. Among the most extreme is a cosmic insect with wings of fire, a nebula that pushes the very definition of a planetary nebula to its limits. The Butterfly Nebula, known formally as NGC 6302, is a masterpiece of destruction. Its wingspan stretches over 3 light years, meaning light itself would take more than 3 years to travel from one shimmering tip to the other. At its heart lies not just a hot white dwarf, but a stellar inferno. The central star is one of the hottest objects ever detected, with surface temperatures soaring beyond 200,000 Kelvin. It is a pinpoint of pure ultraviolet fury. This incredible heat is the paintbrush that illuminates the nebula, but it did not carve its iconic shape. That brutal sculpting was the work of a different force, one we have seen in whispers elsewhere but here screams across the void, immensely powerful bipolar jets. For centuries, these focused beams of material have blasted outward from the stellar system, acting like cosmic sandblasters to hollow out vast cavities in the surrounding gas and dust. They have carved the delicate, intricate filaments that trace the wing's veins and created the pronounced pinched waist that gives the nebula its insect-like appearance. The jets themselves are now faint, their work largely done, but their legacy is this breathtaking, symmetrical sculpture on a scale that dwarfs our entire solar system. Yet for all its searing heat and violent history, the butterfly holds another, colder secret. Within its expansive wings, shrouded by dust, astronomers have found vast, unexpected reservoirs of molecular hydrogen and even water ice. This discovery is counterintuitive. How can fragile water ice and cold molecular gas survive mere light years away from a star so hot it emits primarily lethal ultraviolet radiation? The answer lies in shadow and structure. The dense, dusty torus encircling the central star acts as a colossal shield, blocking the direct UV radiation and creating frigid, sheltered zones in the outer wings where molecules can form and persist. It is a cosmic microclimate where pockets of profound cold exist within a nebula dominated by blistering heat. This complex chemistry tells a story of layered ejection. The star did not shed its envelope in one smooth event. It likely went through phases, first expelling slower, cooler material rich in molecules, and later unleashing the fast winds and jets that then sculpted that earlier material into the butterfly shape. The result is a nebula of stunning contrasts, one of the hottest central stars known, surrounded by some of the coldest molecular material found in such an environment. The butterfly is not a gentle metamorphosis. It is a testament to the chaotic, multifaceted violence of stellar death, where fire and ice coexist in a delicate, wing-shaped balance. The Butterfly Nebula's fiery wings show us violence on a grand scale, but complexity can also be found in a more intimate, layered form. Gaze into the Cat's Eye Nebula, and you are looking at one of the most intricate structures in the entire heavens. Its official designation is NGC 6543, but its popular name captures the unsettling, sentient beauty of its central region, a brilliant, elliptical core surrounded by ghostly concentric rings that fade into the darkness like ripples from a stone thrown into a cosmic pond. When the Hubble Space Telescope first brought this nebula into sharp focus, it revealed a stunning truth. Those rings are not an illusion of light. They are real shells of material ejected by the dying star in a series of regular, powerful pulses. The star did not shed its skin in one continuous heave. Instead, every few hundred years for perhaps 15,000 years, it convulsed, blowing off another dense shell of gas and dust. The result is a fossil record of its final millennia, a layered cosmic onion where each ring marks a separate episode of agony. This pulsed mass loss is a mystery in itself. What could cause a star to cough out its atmosphere with such precise clockwork regularity? The leading theory returns to a familiar actor, a binary companion. The gravitational tug of a nearby star could periodically strip material from the primary, or perhaps the interaction creates regular thermal pulses in the dying star's helium-burning shell, each one triggering a new eruption. But the cat's eye's complexity does not end with its rings. Within its glowing central bubble, Hubble's keen eye resolved a chaotic web of knots, streamers, and violent jets. These are not gentle features, they are the scars of directed, high-speed outflows, likely sculpted by those same binary interactions and powerful magnetic fields. One particularly striking jet blasts out from the core at incredible speed, its tip slamming into a slower-moving shell of earlier ejecta and creating a brilliant, bow shock-like cap of heated gas. This nebula is not a single event, but a palimpsest, a document where one violent history has been written over another. Its serene appearance from a distance dissolves into a portrait of dynamic fury up close, a testament to a death that was anything but peaceful. The cat's eye challenges us to see time in a single image, to understand that what looks like a static sculpture is actually the superimposed frames of a long and violent stellar biography. The cat's eye's layered biography is unique to its star, but to find universal truths, we must look beyond our own galaxy. When astronomers turn their telescopes toward our galactic neighbors, like the majestic Andromeda galaxy or the smaller, irregular Magellanic Clouds, they find planetary nebulae there as well. But these extragalactic nebulae hold a strange and powerful secret. They are not all the same. In our own Milky Way, we see a stunning diversity of shapes and sizes, yet we are limited to a single sample, one galaxy's population of dying stars. By looking outward, we can compare, and the differences are telling. In the large and small Magellanic Clouds, which are satellite galaxies of our own with lower concentrations of heavy elements, planetary nebulae often appear brighter in certain wavelengths than their Milky Way counterparts. This is a direct clue about their chemical makeup and the mass of their central stars, tied to the different evolutionary histories of these galaxies. Because they are all roughly the same distance from us, comparing their apparent brightness becomes a powerful tool. This leads to one of their most valuable cosmic roles. Astronomers realize that the very brightest planetary nebulae in any given galaxy have a remarkably consistent peak luminosity. They are not perfect standard candles, but they are reliable enough to serve as distance markers. By finding these brightest nebulae in a distant galaxy and measuring how dim they appear, scientists can calculate how far away that galaxy is, stepping out across the vast intergalactic voids. But the strangeness lies in the inconsistencies. When this method is applied, sometimes the results are slightly off from other distance measurements. The reason, the planetary nebulae themselves are not identical from galaxy to galaxy. Their intrinsic brightness depends on the chemistry and age of the stars that formed them. A galaxy like Andromeda, which is similar to the Milky Way, produces planetary nebulae that behave in a familiar way. But in a galaxy with a different history of star formation and chemical enrichment, the nebulae will have different properties. So, these glowing shrouds do more than just measure distance. They become forensic tools. By studying populations of planetary nebulae in different galaxies, we can read the history of those galaxies, the ages of their stars, the abundance of elements like oxygen and nitrogen in their systems, and the mass distribution of stars that are now reaching the ends of their lives. Each nebula is a fossil, and by comparing fossils from different galactic dig sites, we are piecing together a broader story of how galaxies live, evolve, and ultimately how their stars die. The humble planetary nebula, once seen as a mere stellar tombstone, becomes a key to mapping the cosmos and understanding its varied evolution. That galactic fossil record can sometimes take the form of a cosmic wobble frozen in light. NGC 2371 is not a single coherent bubble, but a pair of glowing lobes that sit slightly askew from one another, like two soap bubbles blown from a wand that drifted apart before they could merge. This is the double bubble nebula, and its peculiar misalignment is a direct message from a wobbling heart. In most bipolar nebulae, the two lobes are symmetrical, aligned along a single axis as if shot from a stable cannon. Here, that symmetry is broken. The lobes are distinct, separated by a dark lane, and their axes seem subtly shifted. This is not a mistake in the ejection, it is a signature. Astronomers interpret this structure as the fossilized record of a precessing jet. Imagine a spinning top as it begins to slow down. Its axis doesn't stay perfectly vertical, it starts to wobble in a slow, conical motion. Now replace that top with a binary star system at the center of a dying star. If the accretion disk feeding the jets is itself tilted, or if the star's orbits are complex, the entire engine can wobble or precess over time. The jets it fires are not steady, unwavering beams. They sweep across the sky like the beam of a lighthouse. As the central engine precessed, its high-speed jets would have carved out cavities in the surrounding gas, but each sweep would carve in a slightly different direction. The result, after thousands of years, is not a clean pair of cavities, but two overlapping or offset lobes, a double bubble. NGC 2371 is a three-dimensional fossil. By studying the exact shape and orientation of its lobes, we can effectively rewind the motion of its central engine, calculating the period and angle of that ancient wobble. It transforms the nebula from a static picture into a dynamic clock, its frozen gas tracing the precise dance of a binary star system in its final, most violent act. The violent interaction shaping these nebulae is not just visible in light, it screams across the spectrum in high-energy radiation. Discovery 24 reveals a source of power we cannot see with our eyes. Many planetary nebulae are surprisingly bright in X-rays. This was an unexpected find. For decades, these objects were studied through their beautiful optical and radio glow, the gentle fluorescence of their gas. X-rays are the signature of extreme violence, of matter heated to millions of degrees. They come from the searing coronas of active stars or the frenzied accretion disks around black holes. So what were they doing emanating from what appeared to be serene clouds of gas? The answer lies in the collision of two different eras of a star's death. Imagine the scene. First, the slow, ponderous wind from the red giant phase drifts outward, a vast shell of relatively cool material. Then, much later, the exposed white dwarf core revs up its engine, blasting space with a ferocious wind of charged particles moving thousands of kilometers per second. This fast wind does not gently push the older material. It catches up to it and slams into it with unimaginable force. That collision zone is a site of cosmic violence. The gas at the interface is compressed and heated instantaneously to temperatures in the millions of degrees, hot enough to emit the penetrating X-rays our telescopes now detect. In many nebulae, this creates a hot bubble inside the cooler shell, a blistering interior that shapes the entire structure from within. The X-ray glow often outlines the inner walls of the nebula's lobes or fills the central cavity, providing a direct map of where the present is violently rewriting the past. This discovery transforms our understanding of the energy at play. The serene glow we see is just the visible aftermath of a continuous, high-energy impact, a shock wave that is still propagating, still heating, and still sculpting the nebula's final form. The X-ray glow of colliding winds reveals a continuous violence, but some stellar deaths unfold in distinct, punctuated chapters. The Southern Crab Nebula is a cosmic timepiece, its intricate shape a record of separate explosive events. Officially catalogued as He2104, this object does not look like a traditional crab. Instead, it resembles a delicate, nested hourglass, a smaller, brighter structure set within a larger, fainter one. For years, its precise form was a beautiful enigma. Hubble Space Telescope images resolved the mystery, showing that this is not one nebula, but two, launched by the same central star system at different times in the distant past. The mechanism is a specific and dramatic kind of stellar partnership. At the heart of the Southern Crab lies a symbiotic binary system, a dense white dwarf and a bloated red giant locked in a gravitational embrace. The white dwarf pulls a stream of hydrogen-rich gas from its giant companion. This material doesn't fall quietly. It accumulates on the white dwarf's surface until it reaches a critical temperature and pressure, triggering a runaway thermonuclear explosion. This is a nova-like outburst, a titanic blast of energy. But instead of exploding in all directions, the geometry of the system focuses the eruption into two powerful, opposing jets that scream out from the poles of the accretion disk. These jets plow through any surrounding material, carving out a bipolar cavity, an hourglass shape. The evidence suggests this has happened at least twice. Thousands of years ago, the first major eruption blasted out the larger, fainter hourglass we see as the crab's outer legs. Then, after a long celestial silence, the cycle repeated. The white dwarf gathered fresh fuel, erupted again, and fired a new set of jets. These newer, faster jets shot through the interior of the older nebula, carving the smaller, brighter inner hourglass that forms the crab's body. The result is a layered sculpture, a fossilized timeline of two separate cataclysms. The Southern Crab is not a static monument, but a stop-motion film of stellar resurrection and repeated violence, proving that some stars do not die with a single sigh, but with a series of carefully spaced, earth-shattering screams. The serene glow of a nebula is a brilliant lie. We have learned that these objects are sculpted by violent collisions and hidden companions, but their very substance holds another secret. They are not just hot, ionized gas. Discovery 26 shatters that simple picture, revealing planetary nebulae as vast reservoirs of cold molecular gas and dust. This is a profound contradiction. How can fragile molecules survive mere light years away from a star blasting out lethal ultraviolet radiation? The answer lies in shadow and structure, in the dense, dark tori and clumps we have seen sculpting these forms. Within these sheltered zones, temperatures plummet, allowing atoms to link together. Astronomers, using radio and infrared telescopes that see the cold universe, have mapped enormous halos of molecular hydrogen, H2, the basic fuel of stars. They have detected carbon monoxide, CO, a classic tracer of cold, dense gas. In some nebulae, they have even found signatures of complex hydrocarbons, the carbon chains that are precursors to the building blocks of life. This dust and cold gas is not a minor component. In many cases, it contains the majority of the nebula's mass, the very material that was missing from our earlier accounting. This cold component plays several crucial, hidden roles. First, the dust acts as a cosmic coolant. As the dust grains absorb the star's visible and ultraviolet light, they heat up and re-radiate that energy away as infrared light, effectively siphoning heat out of the nebula and allowing the gas to remain cold. Second, the dust grains themselves are microscopic chemical factories. Their surfaces provide a place where atoms can meet, stick, and react, forming molecules that could never assemble in the sparse gas of space alone. Finally, this dust can completely obscure our view. In many young planetary nebulae, the central star is completely hidden behind a thick, dusty waste, visible only because its fierce radiation lights up the lobes above and below the dark belt. This discovery forces a complete revision. A planetary nebula is not a single entity of hot gas. It is a multi-phase ecosystem with searingly hot shock fronts, warm fluorescing gas, and frigid molecular clouds all coexisting, one inside the other, born from the same dying star. The beautiful visible nebula is just the luminous skin of a much colder, darker, and more chemically rich body. The cold, complex ecosystems of most nebulae make the existence of Able 39 all the more startling. Here is a planetary nebula that defies every rule of asymmetry we have just explored. Floating in the constellation Hercules, Able 39 is a near-perfect sphere of glowing gas, a celestial soap bubble of breathtaking simplicity. Its symmetry is so precise it seems almost artificial against the chaotic backdrop of the cosmos. This is Discovery 27, and its very perfection is a profound mystery. In a zoo filled with butterflies, hourglasses, and cat's eyes, why is this one object a simple, round ball? The answer lies in what is missing. Astronomers believe Able 39 is the fossil of a star that died utterly alone. It likely had no binary companion to gravitationally churn its ejector, no rapid rotation to flatten its form, and no strong magnetic field to channel its outflow. Its death was a solitary, quiet, and remarkably uniform event. The star simply swelled into a red giant and then gently shed its outer layers in a smooth, spherical wind, like a sigh expanding equally in all directions. When its core later heated up, it illuminated this pristine shell, creating this cosmic marble. Studying Able 39 is not about marveling at complexity, but about appreciating the baseline. It serves as a critical control in the grand experiment of stellar death. By examining this perfectly simple case, astronomers can isolate the variables. They can say with greater certainty that the bizarre shapes of other nebulae are not random. They are the direct fingerprints of the invisible forces we have discussed, the gravitational pull of a companion, the whip of a magnetic field, the spin of a stellar core. Able 39's serene beauty reminds us that the default state of a dying sun-like star, left entirely to its own devices, might indeed be a perfect sphere. Every other shape is a signature, a story written by hidden actors upon that simple, spherical canvas. That perfect cosmic marble is a rare exception. Far more often, the chemistry of a dying star paints its nebula in wild, unexpected colors. A faint greenish glow in the telescope eyepiece might signal something far stranger than a simple hue. Some compact planetary nebulae emit a spectral signature that is bizarrely familiar to astronomers studying the deepest reaches of the cosmos. Their light shows an intense, specific emission line from doubly ionized oxygen, a brilliant green wavelength that leaps out from the spectrum. This exact same, overpowering fingerprint is the defining feature of an entirely different class of object, the green P galaxies. These are not nearby stellar remnants, but entire dwarf galaxies billions of light-years away, caught in a frenzy of star formation so intense it lights them up like emerald fireflies in the deep field surveys. The connection is a cosmic coincidence of profound significance. It means the same fundamental physical process, ferocious ultraviolet radiation, violently stripping electrons from oxygen atoms, is at work in two utterly different environments. In a planetary nebula, the ultraviolet source is a single, searing white dwarf. In a green P galaxy, the radiation comes from thousands of brilliant, newborn massive stars screaming their lives away in short, violent bursts. The scale could not be more different, a stellar corpse versus a galactic nursery. Yet, to our telescopes analyzing light, they can appear chemically identical for a brief, luminous moment. This spectral echo tells us that the universe often reuses its most effective tools. Ionization is a universal brush, and oxygen is a common paint. Whether the canvas is the funeral shroud of a single star or the chaotic birth cloud of a million suns, the resulting masterpiece can share the same striking color. This strange link is a reminder that the laws of physics are democratic. They operate with the same relentless consistency from the intimate death of a star in our galactic backyard to the colossal stellar baby boom in a galaxy so distant its light is a fossil from the early universe. That spectral echo across cosmic scales reminds us how fleeting these luminous stages truly are. Most planetary nebulae change on timescales measured in millennia, far too slow for any human observer to perceive. But one nebula refuses to follow that rule. The Stingray Nebula, catalogued as Hen 31357, is the youngest planetary nebula ever identified. Its youth is not just a label, it is a visible, dramatic transformation happening before our eyes. In the cosmic blink of just 2 decades, the Hubble Space Telescope captured this object literally fading and changing shape. Images from the 1990s show a bright, compact nebula with distinct wing-like lobes. By the 2000s, those same lobes had noticeably dimmed and their structure had become more diffuse and ragged. The central star itself also cooled much faster than any model predicted. This is like watching a time lapse of a flower wilting, but for a stellar corpse. The Stingray offers an unprecedented real-time laboratory. For the first time, we are not studying a fossilized end state, but witnessing the volatile infancy of a planetary nebula as it unfolds. This rapid evolution suggests the early phases are far more chaotic and unstable than we ever assumed. The intense ultraviolet flash that lights up the nebula may be incredibly brief, and the subsequent cooling and expansion of the gas happens in a frantic rush. The Stingray's changes force us to rewrite the opening chapters of the nebula's life story. It implies that many of the beautiful, stable structures we see in older nebulae are the calm after a storm, the settled remnants of a violent and fleeting youth. By studying this cosmic toddler, we gain crucial insight into what all planetary nebulae must have gone through in their first centuries. A frenetic period of adjustment that was, until now, completely hidden from our view. The very definition of a planetary nebula is built upon a specific kind of death, a slow, elegant fading reserved for stars like our Sun. Yet the cosmos delights in breaking its own rules. Discovery 30 asks a startling question: could a massive star, a titanic furnace destined for a supernova, ever produce something that looks like a planetary nebula? The textbook answer has always been a firm no. A massive star ends its life in a cataclysm, blasting its remains across light years in a violent supernova remnant, a chaotic cloud of shattered elements. A sun-like star ends with a gentle puff, a glowing shroud lit from within. These are 2 different stories, 2 different ends of the stellar spectrum. But theoretical models are now painting a more nuanced picture. Under very specific and rare conditions, a massive star might briefly mimic the death of its smaller cousin. Imagine a star 8 or even 10 times the mass of our Sun. Its core is a furious factory, fusing elements all the way up to iron. In its final millennia, it becomes a red supergiant, an unstable, bloated monster. If this star loses its outer hydrogen envelope slowly and steadily through powerful winds before the core collapses, it could expose a hot, dense core of helium or carbon-oxygen. This exposed core, much hotter and more massive than a typical white dwarf, could then flood the surrounding, slowly expelled material with ultraviolet radiation. For a fleeting cosmic moment, perhaps just a few thousand years, the result would look uncannily like a planetary nebula, a glowing, ionized shell of gas around a brilliant central star. But this would be a planetary nebula in name only, a brilliant imposter. The central engine would not be a cooling white dwarf, but a ticking time bomb, a massive wolf-rayed star or a pre-supernova core on the brink of collapse. Soon, perhaps in another 10,000 years, that core would detonate in a supernova, utterly obliterating the delicate nebula it had just created. The supernova blast wave would overtake and shred the glowing shell, mixing it violently with new, heavier elements like nickel, gold, and uranium forged in the explosion. What we would witness is a hybrid, a two-act tragedy. First, a beautiful, deceptive farewell, and then the true world-ending finale. This theoretical possibility blurs a line we thought was solid. It suggests that the beautiful planetary nebula phase might not be a peaceful end, but a brief, serene prelude to a far greater violence, a final, glowing deep breath before the ultimate scream. The ghostly tadpoles of the Helix Nebula are more than just beautiful shadows. Recent observations have peeled back another layer of their mystery, revealing these cometary knots may possess a hidden gravitational heart. For a long time, the prevailing theory held that the knots were simply denser clumps in the expanding shell, shaped by external radiation pressure like sand dunes under a steady wind. But this picture could not explain everything. The knots are incredibly stable, maintaining their coherent structure over vast distances as they stream away from the central star. They should be shredded apart by the violent forces around them, yet they persist. This stability points to an internal anchor, a force holding them together from within. The startling new hypothesis is that these knots are self-gravitating. This means each individual knot, a cloud of gas and dust twice the size of our solar system, has enough mass for its own gravity to bind it together against the disruptive pressure of the stellar wind and radiation. Think of them not as wisps of smoke, but as miniature, cohesive worlds of gas. Their gravity would act as a protective shell, allowing an even denser core to form inside. Within that shielded heart, conditions could be cool and dense enough for molecules to form and survive. Simple molecules like molecular hydrogen, or even more complex carbon-bearing compounds. This transforms our understanding of their ultimate fate. If the knots are gravitationally bound objects with dense molecular cores, they might not simply dissipate into a thin haze. Instead, as they drift completely free of the nebula over hundreds of thousands of years, they could journey into the interstellar medium as intact comet-like bodies. Each knot would become a dark, frozen traveler, a cosmic iceberg carrying within it the enriched chemistry of its parent star's death. The Helix Nebula, then, is not just a glowing eye. It is a launching pad, casting billions of these tiny, self-contained chemical packages into the galactic void, where they might one day seed other clouds with the raw ingredients for new stellar systems. The visible light that paints these nebulae is only a fraction of their story. To see the rest, we needed new eyes, instruments that could peer through the veils of dust to the cold truth beneath. The Spitzer Space Telescope, with its infrared vision, did exactly that, and its findings were a quiet revolution. Where our optical telescopes saw a beautiful, glowing ring, Spitzer often saw a vast, faint halo of cold dust stretching far into the darkness. This was the missing mass made visible. These immense dusty shrouds, sometimes 10 times larger than the bright central nebula, are the fossil records of a star's earlier, calmer life. Long before the dramatic final act, while the star was still a stable red giant, it was shedding material in a slow, steady wind. This dust drifted away for millennia, cooling into a frigid, invisible envelope. Only when the later ultraviolet flash arrived did it illuminate the inner part of this structure, creating the iconic nebula we know. The outer halo remained, a ghostly fingerprint of that earlier, more patient era of mass loss. Spitzer showed us that the brilliant nebula is just the inner heart of a much larger, colder, and older body, a cosmic iceberg whose visible tip we had mistaken for the whole. Now, the James Webb Space Telescope has taken up this infrared watch with unimaginable sensitivity. Its promise is to transform these dusty halos from faint smudges into detailed chemical maps. Webb can detect the specific infrared fingerprints of molecules that Spitzer could only hint at. Within those frigid, sheltered zones, we anticipate finding not just simple carbon monoxide or dust, but a zoo of complex organic molecules, the polycyclic aromatic hydrocarbons, the fullerenes, and perhaps entirely new forms of carbon-based chemistry we have not yet named. These molecules form on the surfaces of dust grains in the cold, dark outskirts of the nebula, far from the destructive ultraviolet glare of the central star. Webb is essentially a cosmic chemist, able to analyze the contents of these frozen interstellar warehouses. What will it find? It may trace the full journey of carbon, from its forging in the stellar core to its assembly into intricate molecular chains and cages in the cold expanse. Each planetary nebula halo could be a unique recipe book for complex chemistry, and Webb is reading the ingredients for the first time. This isn't just about understanding death, it's about cataloging the legacy. We are on the verge of seeing, in exquisite detail, exactly what raw materials, including the potential precursors to life's building blocks, a dying star packages and ships out into the galaxy. The universe is never truly silent, even in death. Long before the brilliant nebula forms, the swollen red giant star enters a phase of profound internal music. This is the period of stellar pulsations, a rhythmic heartbeat that will ultimately shape its final shroud. Deep within the star's churning layers, powerful pressure waves, essentially sound waves of unimaginably low frequency, ripple outward from the core. They travel through the star's vast interior, growing in strength until they reach the tenuous outer atmosphere. Here, these waves become starquakes, rhythmic convulsions that push the star's gaseous envelope outward in great, heaving pulses. Each pulsation acts like a cosmic gong strike, sending a spherical shockwave through the star's atmosphere. This shockwave does more than just make the star brighten and dim. It lifts material, literally helping gravity let go. With each rhythmic push, another layer of the star's outer self is lofted a little further into space, making it easier for the relentless stellar wind to carry it away. This pulsation-driven mass loss is a more controlled, periodic process than a simple, steady wind. It is the dying star's final, resonant song, and its rhythm is written into the nebula it leaves behind. Those haunting concentric rings in the Cat's Eye Nebula, the nested shells seen in the Egg Nebula's light echoes, these are the fossil records of that song. Each perfect ring corresponds to a major pulsation event, a moment when the star's internal music reached a crescendo and ejected a distinct shell of material. By counting the rings, astronomers can estimate the tempo of the star's final millennia, a rhythm often measured in centuries between each profound beat. This pulsating mechanism provides an elegant answer to how a star can shed its skin in such orderly, discrete layers. It is not a chaotic explosion, but a rhythmic exhalation, a controlled release conducted by the star's own internal vibrations. The beautiful, layered nebulae we admire are therefore more than just static sculptures. They are phonograph records, their grooves etched not by a needle, but by spherical sound waves, preserving the tempo and intensity of a star's last, deep-throated song for all eternity. The rhythm of a star's final song can sometimes be focused into a piercing, narrow scream. In the constellation Ophiuchus, the twin-jet nebula offers a masterclass in stellar precision. Catalogued as M29, this object is not a gentle, expanding bubble. It is a stark, ethereal figure, a glowing hourglass with two narrow, ghostly wings that stretch into the darkness. Its popular name is perfectly literal. At its heart, two powerful, high-speed jets blast outward in opposite directions, traveling at speeds estimated to exceed 300 kilometers per second. These are not the broad, fanning outflows of some nebulae, but tightly collimated beams like cosmic blowtorches. They have carved out the nebula's remarkably thin waist and inflated the two vast, wing-like lobes that give it its insectile appearance. This is a nebula sculpted not by a gentle wind, but by surgical, directed violence. The source of that violence is now widely accepted to be a hidden gravitational dance. At the center of M29 lies not one star but two, a binary system where a hot white dwarf orbits a cooler, dying giant. The white dwarf's fierce gravity pulls a stream of gas from its bloated companion. But this stolen material does not fall directly onto the star. Instead, it spirals inward, forming a superheated, spinning disk of matter called an accretion disk. This disk is the engine, and its physics are universal. As material in the disk swirls at incredible speeds, friction and magnetic fields can launch a portion of it away from the system, focused into those two narrow jets erupting from the disk's poles. The twin-jet nebula, therefore, is far more than a beautiful curiosity. It is a scaled-down analog to the most energetic jet phenomena in the cosmos. The same basic process, accretion onto a dense central object, creates the relativistic jets that scream from the supermassive black holes at the centers of galaxies. Of course, the energies involved are astronomically different. A black hole's jets move at nearly the speed of light and can be millions of light years long. In M29, the central object is a mere white dwarf, and its jets are only a few light years long. Yet, the underlying blueprint is eerily similar: a dense core, a feeding disk, and focused bipolar outflows. Studying this delicate nebula allows us to test our fundamental models of how accretion and jet launching work in a laboratory close enough to see in stunning detail. It proves that the universe often uses the same tools, whether it is shaping the funeral shroud of a star or governing the most powerful engines in existence. The delicate jets of the twin-jet nebula are more than a cosmic sculpture, they are a delivery system. This chemical legacy is the most profound discovery of all, a truth that connects the death of distant stars directly to you. Every atom of carbon in your body, every molecule that forms the foundation of life on Earth, was forged in the heart of a star and likely scattered into the galaxy by an event just like this. Planetary nebulae are the primary galactic recyclers for these mid-weight elements. As a sun-like star dies, its final convulsions dredge up material from its interior where nuclear fusion has been at work for eons. This process transforms simple hydrogen and helium into heavier elements like carbon, nitrogen, and oxygen. The star's violent winds and ejections then hurl this newly forged material into space, enriching the vast clouds between stars. This enriched gas is the raw material for the next generation of stars, planets, and ultimately, living things. Consider the carbon in the graphite of your pencil, the diamond in a ring, or the complex chains in every cell of your body. That carbon was not present in the primordial universe after the Big Bang. It had to be created, and the dominant factories for carbon in our galaxy are stars like the ones that become planetary nebulae. When you look at a nebula's beautiful glow, you are witnessing the moment these essential ingredients are packaged and shipped. The nebula itself is the brilliant label on the crate, but the precious cargo inside is the enriched gas and dust that will one day collapse into new solar systems. Our own solar system formed from a cloud that had been seeded by the deaths of many previous stars. So, in a very literal sense, you are made of stardust, and a significant portion of that dust was delivered by the beautiful, violent final acts of stars that died long before our sun was born. This transforms our perspective entirely. These objects are not merely tombs, they are cosmic gardens, fertilizing the galaxy with the very elements that make rocky worlds, oceans, and life itself possible. The next time you gaze at an image of a glowing nebula, remember you are not just looking at a distant spectacle. You are looking at your own ancient history written in light and gas. The brilliant chaos of a young nebula can sometimes mirror the birthplaces of worlds. Within the turbulent heart of NGC 7027, a nebula so young it still crackles with violent energy, the Hubble Space Telescope spotted something hauntingly familiar. Scattered throughout its glowing interior are small, teardrop-shaped structures, each one with a dark head and a bright, fanning tail that streams away from the central star. To astronomers, these shapes were an instant echo of a famous cosmic nursery. They look almost identical to the proplyds or protoplanetary disks found in the Orion Nebula. In Orion, those dark heads are dense cocoons of gas and dust surrounding infant stars, with their luminous tails created as the fierce ultraviolet radiation from nearby massive stars boils away their outer layers, a process called photoevaporation. But here, in a planetary nebula, there are no newborn stars. So what are we seeing? The answer lies in a destructive form of cosmic mimicry. In NGC 7027, the dense knots are not stellar wombs, but likely clumps of material recently ejected from the dying star itself. They are survivors, pockets of gas and dust that are slightly denser and cooler than their surroundings. The central star, a searingly hot white dwarf, bombards everything around it with intense ultraviolet radiation. This radiation acts like a cosmic blowtorch, stripping atoms apart and heating the gas. The dense knots can withstand this assault longer than the thin gas around them. They act as shields, casting long shadows of protection behind them. The material in that shadow remains neutral and cool, forming the dark head. Meanwhile, the radiation relentlessly erodes the knot from the side facing the star, boiling off material and ionizing it, which creates the bright, streaming tail that points directly away from the destructive source. It is a stunning case of parallel cosmic processes. In Orion, the process is about birth, where the harsh light of young stars sculpts the material from which planets may form. In NGC 7027, the process is about death, where the harsh light of a stellar corpse sculpts the debris of its own destruction. The same physics, the same beautiful, tear-shaped structures appear at both ends of the stellar life cycle. This discovery blurs the line between creation and destruction. It suggests that the universe has a limited palette of forms, and whether you are building a solar system or dismantling a star, the forces of radiation and gravity will often write their signatures in the same elegant, heartbreaking shapes. That sculpting of debris by starlight reveals a critical, hidden transition in the star's final act. For thousands of years, the dying red giant, now called an asymptotic giant branch star, has been losing mass in a slow, dense, and dusty outflow. This is the superwind, a ponderous exhalation where molecules and soot form easily in the relatively cool, expanding envelope. It carries away the bulk of the star's remaining hydrogen, puffing it outward at a leisurely pace of perhaps 10 to 30 kilometers per second. Then something profound and sudden happens. The star's core, having finally exhausted its nuclear fuel, collapses down to a white dwarf. This tiny, searing hot ember now unleashes a completely different kind of wind, a fast, tenuous blast of charged particles screaming outward at thousands of kilometers per second. This is not a gentle breeze, but a hurricane of pure energy. The planetary nebula we see is born precisely in the violent collision zone between these two eras. The fast wind catches up to the slower, denser superwind material and slams into it. That impact front is a shockwave of cosmic proportions, heating gas to millions of degrees and compressing it into the luminous shells and lobes that define the nebula's shape. It is like a speeding bullet striking a wall of fog, creating a brilliant, structured flash at the moment of impact. Yet, the exact trigger for this dramatic shift remains one of the great unsolved puzzles in stellar evolution. What flips the switch from a slow, dusty superwind to a furious, ionized gale? Is it the final, violent shudder of the helium-burning shell deep within the star? Does the sudden exposure of the blistering core itself initiate the change? Or does the interaction with a binary companion fundamentally alter the star's ability to hold onto its atmosphere? This mystery is at the very heart of the nebula's existence. Without that shift, the superwind would simply drift away as a dark, cold molecular cloud, never to glow. The timing, intensity, and geometry of this transition determine everything about the nebula's final appearance, its brightness, its form, and ultimately, how effectively it seeds the galaxy with new chemistry. We are still deciphering the last, critical command from the star's core that shouts enough and transforms a slow sigh into a brilliant, structured farewell. The universe has a way of turning even a star's final breath into a tool for seeing the impossible. Among the most mind-bending theoretical roles a planetary nebula could play is that of a cosmic magnifying glass, a gravitational lens. This is not about its beautiful glow, but about its sheer mass warping the fabric of space-time around it. According to Einstein's theory of general relativity, any massive object bends the path of light passing nearby. We see this spectacularly with entire galaxies, which can distort the images of galaxies far behind them into brilliant arcs and rings. But could a single dying star's shroud, a cloud of gas and dust, be massive enough to produce a detectable lensing effect? The answer is a tentative, thrilling yes. While the effect would be exquisitely subtle, there is a rare and fascinating possibility. If a planetary nebula drifts directly in front of a distant, point-like background star, the nebula's total mass, the combined weight of its gas, dust, and central star, could very slightly bend and amplify the star's light. We would not see dramatic arcs. Instead, we would detect a tiny, characteristic brightening of that background star as the nebula's gravitational field focuses its light, a fleeting event known as microlensing. Detecting such an event is a monumental challenge. It requires perfect alignment across thousands of light years and instruments precise enough to measure minuscule changes in a star's brightness. To date, a confirmed case of a planetary nebula acting as a gravitational lens remains elusive, a ghost in the data. Yet, the mere possibility is a powerful lure for astronomers. Why? Because gravitational lensing does not care about what is glowing. It measures all the mass present, both seen and unseen. If we could ever measure the lensing effect of a planetary nebula, we could weigh it with near-perfect accuracy. We could finally solve the missing mass mystery not by estimating, but by directly measuring the total gravitational pull. This would tell us exactly how much material is hiding in those dark, cold halos, or even in forms we cannot detect at all. Which brings us to a wonderfully speculative idea. Could some of that unseen mass be something even more exotic, like dark matter? It is a long shot, but a captivating thought. If the progenitor star had a halo of dark matter particles around it, a possibility for some stars that dark matter would still be there, invisibly contributing to the lensing effect. Finding its signature would be a revolutionary connection between the intimate death of a star and the universe's most pervasive mystery. While unlikely, it highlights the profound potential of this idea. A planetary nebula would then be more than a chemical factory or a beautiful sculpture. It would become a precision scale, weighing itself against the light of a distant sun, and perhaps, just perhaps, revealing shadows within shadows. The universe rarely writes its signatures in straight lines. In the southern constellation Musca, a dying star has scrawled a cosmic question mark across the heavens. This is NGC 5189, a planetary nebula whose form defies simple description. It is not a ring, an hourglass, or a butterfly. Instead, it resembles a giant glowing cursive S, or the mathematical symbol for an integral, a shape of such intricate twisting that it seems almost impossible for nature to have created it. Its central region is a chaotic tangle of bright knots and dark lanes, from which two sweeping, curving arms spiral outward in opposite directions, as if some colossal hand had drawn a figure 8 in the sky and then stretched and warped it. This bizarre morphology is not random art, it is a three-dimensional fossil of a wobble. The leading explanation returns to the hidden dance of a binary star system, but with a mesmerizing new detail, precession. Imagine the central binary system as a spinning top. As it spins, its axis doesn't stay perfectly upright. It slowly wobbles in a conical motion. This is precession. Now imagine that this wobbling system is also firing out twin jets of material from its poles. Those jets would not point in a fixed direction. They would sweep across the sky like the beam of a lighthouse, tracing a spiraling pattern over thousands of years. As the dying star expelled its outer layers, these processing jets carved through the cloud, sculpting the gas into those magnificent, curving arms we see today. NGC 5189 is essentially a time-lapse photograph of that celestial wobble, frozen in glowing gas. Each twist and loop in its structure corresponds to a different epoch in the precession cycle, allowing astronomers to essentially rewind the motion and calculate the orbital dynamics of the central stars that have long since faded from view. This integral sign in the sky is therefore more than a beautiful shape. It is a precise mathematical record, a spiraling signature written by gravity itself, proving that even in death, a star's motion can paint a masterpiece of breathtaking geometry. That spiraling signature of gravity will not last. The most profound and strange discovery of all is not about how these nebulae form, but how they end. Their breathtaking beauty is a cosmic illusion of permanence. A planetary nebula is not a monument. It is a mirage, a brief and glorious flash in the multi-billion-year life of a star. From the moment its gas first glows, the clock is ticking. The nebula is born expanding, and it never stops. For 10,000, perhaps 20,000 years, it shines, its intricate shapes held together by the momentum of its own explosion and the fierce wind from its central star. But that wind will eventually falter. The white dwarf's ultraviolet fury diminishes as it cools. The radiation pressure that ionizes the gas and makes it fluoresce weakens. The atoms recombine, their brilliant colors fading. The expanding shell, now traveling at tens of kilometers per second, continues to fly apart. Its density drops catastrophically. What was once a vivid, structured cloud becomes a tenuous, invisible haze. Within perhaps 50,000 years, a mere instant on cosmic timescales, the nebula has dissipated completely, its material mixing and blending with the cold, dark gas of the interstellar medium. The sculpture is gone. All that remains is the enriched legacy of its chemistry, now scattered across light years, waiting to be gathered into a new generation of stars and planets. And at the center of it all, the white dwarf remains. This Earth-sized ember of carbon and oxygen, the star's exposed core, is all that is left. It will shine with a faint white heat for trillions of years, slowly cooling toward absolute zero, becoming a black dwarf, a cold, dark crystal floating in the void. This is the ultimate perspective shift. When we look at the cat's eye or the butterfly, we are not looking at a permanent feature of the galaxy. We are witnessing an event. We have caught the universe in a fleeting act of transformation, a brilliant intermediary stage between a star's death and its complete dispersal. It is a privilege of our place in cosmic time that we can see these objects at all. In another 100,000 years, many of the nebulae we catalogue today will have vanished without a trace. Their central white dwarfs will be faint pinpricks, and their magnificent gas will have become anonymous raw material for the future. This transience makes them all the more precious. They are the universe's fireflies, glowing for a single summer night before disappearing into the dark, leaving behind only the seeds of what is to come. The ghostly echo of a stellar encore was captured not in ancient starlight, but within human memory. In the summer of 1919, as the world recovered from war, a faint star in the constellation Aquila did something impossible. It came back to life. Catalogued as V605 Aquilae, this object was a dim, cooling white dwarf, the corpse of a sun-like star that had died millennia earlier and left behind a faint, expanding planetary nebula known as Abell 58. Then it erupted. Astronomers watching old photographic plates saw it brighten by a factor of nearly 10,000, transforming in mere months from a faint speck into a brilliant beacon. This was not a supernova. It was something far stranger and more precise, a final helium shell flash, the ultimate spasm of a stellar corpse. Deep within the white dwarf, a thin, dormant shell of unburned helium surrounding the carbon-oxygen core had reached a critical pressure and temperature. It ignited in a final, furious burst of nuclear fusion. The energy released was catastrophic, not enough to destroy the star, but enough to resurrect it. The white dwarf violently reinflated, swelling back out to a red giant size in a cosmic blink. For a brief, glorious period, V605 Aquila was born again, a stellar Lazarus shining in the night sky. Today, telescopic observations reveal the breathtaking evidence of this event. We see the large, faint, ancient shell of Abell 58, the original planetary nebula from its first death. And nestled inside it, a much smaller, denser, and younger nebula, recently ejected during the 1919 outburst. This inner nebula holds a crucial chemical clue. It is remarkably poor in hydrogen. Why? Because during its first death, the star expelled almost all of its outer hydrogen envelope. When the final flash occurred, it dredged up material from much deeper layers, helium, carbon, and oxygen, and blasted that into space instead. The result is a nested chemical fossil, an old hydrogen-rich shell and a new hydrogen-poor one, a direct observational record of a star dying twice, each time revealing a different layer of its interior. V605 Aquila is not just a theory. It is a confirmed case, a time-stamped event in our astronomical history that proves the born-again phenomenon is real, and that a star's final chapter can include a violent, brilliant, and deeply revealing postscript. That fleeting brilliance of a stellar encore is often captured in the cold, hard signatures of dust. Among the most stubborn of these cosmic fingerprints is a ghost in the infrared, a spectral line that has defied identification for decades. In the cold, dusty envelopes of certain planetary nebulae, astronomers detect a sharp, prominent emission feature at a wavelength of 21 micrometers. This is not a gentle hum, but a distinct spike in the data, a clear signal that something specific in the dust is absorbing starlight and re-radiating it at this exact infrared color. The problem is, no common substance matches it. The usual suspects, simple silicates, carbon soot, or even the complex PAH molecules do not produce this precise signature. The 21-micron feature is an anomaly, a persistent question mark written in the thermal glow of stellar debris. So what could possibly be emitting it? The leading candidates are exotic crystals forged in the extreme conditions of a dying star's outflow. One strong possibility is titanium carbide, a ceramic-like compound of titanium and carbon that forms at extremely high temperatures. Another is a specific form of silicon carbide, a mineral known on Earth as moissanite. These are not amorphous, fluffy grains. They are thought to be microscopic crystals, perfectly structured lattices of atoms that could vibrate and emit light at this specific frequency when warmed by the central star. Think of them as trillions of tiny, identical tuning forks, all resonating at the same infrared pitch across light years of space. Their existence points to a specialized, high-temperature condensation sequence in the stellar wind, where conditions are just right for these particular minerals to crystallize out of the expanding gas, like snowflakes forming in a frigid, precise cloud. Yet, even with these candidates, the puzzle is not fully solved. Laboratory measurements of these materials have not yet perfectly replicated the exact shape and subtle details of the astronomical feature. This leaves room for other, even more exotic possibilities. Could it be a form of carbon we haven't considered, or a compound involving other heavy elements like magnesium or iron? The 21-micron mystery is more than a technical detail. It is a lesson in cosmic humility. It reminds us that the chemistry of stellar death is a frontier, and that the dust drifting from these stars may be composed of minerals we are only beginning to understand, crystalline messengers from an alien forge. That final, brilliant flash is a violent punctuation mark, but the most dramatic act in a binary star's life often unfolds in a hidden, suffocating embrace. Common envelope evolution is not a gentle dance, but a stellar merger in progress, a desperate struggle for survival that can forge the most extreme shapes in the nebula zoo. Imagine two stars in a close orbit, one swelling into a red giant as it dies. Its outer layers become so distended that they literally engulf its smaller companion. The companion star is now not just orbiting a star, it is plunging through the star's extended atmosphere, a dense fog of hydrogen gas. This is the common envelope phase, and it is a recipe for cosmic chaos. Friction is the engine of catastrophe. As the companion spirals inward through this thick, resisting gas, it transfers orbital energy into the envelope. That energy doesn't vanish. It heats the gas violently and, in most cases, provides the tremendous push needed to eject the entire common envelope into space. The process is brutally efficient. Within a few hundred years, the companion star can spiral from an orbit the size of Earth's down to one smaller than Mercury's, while the red giant's puffy atmosphere is blasted away in a titanic bipolar outflow. The result is often a planetary nebula with an incredibly pinched waist and vast symmetrical lobes, the kind of extreme hourglass shape that defies simpler explanations. The Southern Crab Nebula, with its nested hourglasses, is a prime candidate for a system that underwent not one, but possibly two common envelope episodes. This discovery redefines the power of partnership. It shows that the most breathtaking nebulae are not sculpted by a companion's gentle influence, but by its violent orbital death plunge, a sacrifice of orbital energy that carves a masterpiece from stellar chaos. The universe sometimes winks at us through a veil of gas. Gaze upon the Owl Nebula, and you will meet its haunting, dark-eyed stare. Catalogued as M97, this object is a nearly perfect sphere of faint greenish light floating in the constellation Ursa Major. But what gives it its name and its eerie personality are two unmistakable dark patches, symmetrically placed within the glowing shell like the eyes of a cosmic bird. These are not mere smudges or shadows. They are actual cavities, three-dimensional holes of lower density gas punched through the nebula's fabric. Their perfect symmetry is the key to their origin. These eyes are almost certainly the fossilized imprint of bipolar jets that once screamed from the central star system. For a brief period in the nebula's violent youth, focused beams of material would have blasted outward in opposite directions, carving tunnels through the expanding spherical shell. Like a sculptor drilling into a block of marble, these jets excavated material, leaving behind these clean, circular voids. Then the jets ceased. The central engine shut down or shifted its mode of ejection, leaving the cavities to slowly expand and diffuse within the larger, gentler outflow of the nebula. Today, all that remains is the hollow impression, a negative space that our minds interpret as eyes. This transformation is a profound lesson in cosmic perception. The Owl Nebula's most defining feature is not something that is there, but something that is absent. Its character is defined by an emptiness, a permanent record of a violent directional force that has long since fallen silent. Those dark eyes are not watching us. They are looking back in time, showing us the precise axis along which the star's death was once focused, a direction now lost to the steady, spherical expansion of the rest of its shroud. The brilliant nebula fades, but the story of its core is just beginning. Discovery 45 reveals that the white dwarf left behind is not a silent, cooling ember. Many of these stellar remnants are variable stars, their light pulsing with a precise, rhythmic beat. These are not the violent convulsions of a dying giant, but the subtle, resonant vibrations of a dense, crystalline sphere settling into its eternal rest. Astronomers detect these changes as tiny, regular fluctuations in brightness, sometimes by just a fraction of a percent over periods of minutes. This field of study is called asteroseismology, the art of listening to the music of the stars. By measuring the precise frequencies of these pulsations, scientists can perform a kind of cosmic ultrasound on the white dwarf. Each vibration mode probes a different depth within the star, revealing secrets no telescope could ever see directly. The data tells them about the thickness of the outer hydrogen or helium layers, the composition of the carbon-oxygen core, and even the star's rotation rate. It is as if the white dwarf is ringing like a bell, and the tone of that ring tells us exactly what it is made of and how it is structured. This is profoundly important because it gives us a direct window into the endpoint of stellar evolution for Sun-like stars. The planetary nebula showed us the beautiful expulsion of the outer layers, but asteroseismology of the white dwarf shows us the precise condition of the dense remnant that remains. By studying these pulsations across many white dwarfs, we are effectively taking a census of stellar corpses, learning the distribution of masses and compositions that stars leave behind. This data, in turn, helps us refine every step of the models that predict how stars like our own Sun will die. The gentle, rhythmic pulsing of a white dwarf is the final, quiet heartbeat of the system, a coded message about the furnace that once was, long after its brilliant funeral shroud has dissipated into the darkness. The furnace at the heart of NGC 2440 is a stellar monster. This white dwarf's surface temperature soars beyond 200,000 Kelvin, making it one of the hottest stellar corpses ever recorded. Its ultraviolet rays should, in theory, sterilize its surroundings, breaking apart any delicate chemistry. Yet, when astronomers peer into the nebula's glowing lobes with infrared eyes, they find a startling contradiction. The dust here is not simple soot. It is a complex chemical inventory, a mixture of the organic and the crystalline that defies the searing environment. The signatures are unmistakable. Polycyclic aromatic hydrocarbons, those flat chicken wire molecules of carbon and hydrogen, emit their broad infrared hum. Alongside them, shining with sharp, precise spectral lines, are crystalline silicates minerals like forsterite, a magnesium-rich cousin of olivine found in Earth's mantle. This is a bizarre partnership. PAHs are thought to form in relatively cool, carbon-rich environments, the sooty smoke of stellar fires. Crystalline silicates, on the other hand, require high temperatures to form their ordered lattice structures, but they also need to cool slowly to avoid becoming amorphous glass. Finding them together in the same nebula, illuminated by such a ferocious star, is a chemical puzzle. It tells a story of a star that did not die in a single, uniform event. The likely explanation is a layered, sequential death. First, during its earlier red giant phase, the star may have been oxygen-rich, allowing silicate dust to condense in its cooler, expanding atmosphere. Some of that dust, shielded in dense clumps, could have been heated just enough by the star's warmth to anneal into crystals without being destroyed. Later, as the star evolved, it may have become carbon-rich, dredging up newly forged carbon from its interior. This carbon then coated existing grains or formed new PAH molecules in the cooler, outer reaches of the nebula, far from the central inferno. The result is a cosmic cocktail, a mineral and organic dust cloud all at once. NGC 2440 is not just a hot star and a pretty shell. It is a forensic site where the infrared fingerprints in the dust reveal a detailed history of the star's final chemical changes, a layered testament to how a star can rewrite its own composition right up to the very end. Even the name Ghost of Jupiter carries a spectral chill. This planetary nebula, catalogued as NGC 3242, floats in the constellation Hydra, a brilliant inner eye surrounded by faint, ethereal shrouds. Through a backyard telescope, its central region appears as a vivid, slightly elongated disk of greenish-blue light, reminiscent of the gas giant planet that inspired its haunting nickname. But this ghost is more than a pretty apparition. Its true scientific value lies in the layers that casual observers often miss, the faint, concentric halos that stretch far beyond its bright core, like the fading echoes of a scream. These multiple shells are a fossilized timeline, a direct record of the star's episodic death. Long before the final, dramatic ejection that formed the brilliant inner nebula, the star experienced several earlier, quieter episodes of mass loss. Each of these events blew off a shell of material which drifted outward for thousands of years, cooling and fading. When the star's core finally became hot enough to unleash its ultraviolet flash, it lit up only the innermost, densest shell, the one we see so brightly. The older, outer halos remained, too tenuous to glow as intensely, but detectable to sensitive instruments as ghostly rings of hydrogen emission. This layered structure makes the ghost of Jupiter a perfect cosmic laboratory. Because it is relatively close and bright, astronomers can dissect its light with extreme precision. They can map how the intensity of the ultraviolet radiation from the central star decreases with distance, ionizing different elements at different depths within the nebula. They can measure the expansion speeds of each separate shell, learning whether the star's earlier outbursts were gentler or more violent than its last. By studying this one object in detail, we gain a standard model, a benchmark against which fainter, more distant nebulae can be compared. The ghost of Jupiter, therefore, is more than a celestial spectre. It is a calibrated instrument, its multiple shells acting like a series of frozen shockwaves, allowing us to replay the star's final millennia and measure the changing strength of its dying breath. The Medusa Nebula is a ghost in the night sky, a sprawling, faint tangle of filaments so tenuous it evaded detection for centuries. Catalogued as Able 21, this ancient planetary nebula is a cosmic elder, its brilliant phase of life long since over. To see it at all required the patience of long-exposure photography, where a camera's shutter stays open for hours, gathering every last photon of its dying light. What emerges from that patient gaze is not a brilliant ring or a sharp hourglass, but a web of faint, greenish tendrils, like the serpentine hair of its mythological namesake, drifting apart in the void. This is not a nebula in its prime, it is a nebula in its final act of dissipation. The Medusa's filamentary structure is a direct snapshot of a process called hydrodynamic instabilities. Imagine blowing a smoke ring. At first, it holds a clean, circular shape, but as it expands and interacts with the still air around it, it begins to waver, to ripple, and finally, to fray into wisps and tendrils before vanishing completely. On a cosmic scale, that is precisely what is happening to the Medusa Nebula. Its once coherent shell, having expanded for perhaps tens of thousands of years, has grown so thin that subtle forces are tearing it apart. The pressure from the surrounding interstellar medium, the slight variations in density within the shell itself, and the relentless pull of gravity from the galaxy all conspire to stretch and shred the glowing gas into these delicate, filamentary strands. Studying the Medusa is like finding the faded, crumbling pages of a very old book. It tells us the ultimate fate of every planetary nebula we have marveled at. The cat's eye, the butterfly, the ring, all those brilliant, structured forms will, given enough time, share this same fate. They will expand until their density drops to near nothing, their shapes will fragment into faint, ghostly webs, and their light will fade into imperceptibility as their atoms quietly blend back into the galactic reservoir from which they came. The Medusa Nebula is a poignant reminder of the profound transience of cosmic beauty. It shows us the breathtaking structures we admire are not monuments, but moments, brilliant flashes in the dark that are already, from the moment of their birth, beginning to unravel. Yet the most ancient stellar cities in our galaxy hold their own rare and precious gems. Globular clusters are dense, spherical swarms of hundreds of thousands of stars, all born together in the distant infancy of the Milky Way. They are cosmic retirement homes, their populations dominated by ancient, low-mass stars that have been quietly burning for over 10 billion years. In such an old and crowded environment, the brief, brilliant flash of a planetary nebula should be an extreme rarity. The massive stars that could produce them died off eons ago in spectacular supernova. only the slowest burning sun-like stars would still be reaching their ends now. And that is precisely what makes the few planetary nebulae found in globular clusters so extraordinarily valuable. They are cosmic stopwatches confirming the slowest possible stellar life cycles. In the Great Cluster M15, a faint blue-green smudge was identified and named PS1. It is a planetary nebula. Its existence tells a profound story. The star that created it was one of the lowest mass stars capable of ever becoming a planetary nebula, a star that took the absolute maximum time to run through its nuclear fuel. For over 12 billion years, it lived a quiet life in the cluster. Then, only recently in cosmic terms, perhaps in the last 50,000 years, it finally reached its end. The presence of PS1 provides a critical benchmark for astronomers. It pins down the absolute lower limit for the mass of a star that can produce a visible nebula. Any star with less mass would burn so slowly and coolly that it would simply fade into a white dwarf without the dramatic ejection phase, becoming a dark, helium-rich ember known as a helium white dwarf. So this faint nebula in M15 is a boundary marker defining the edge of possibility for stellar death as we know it. Another example found in the cluster M22 reinforces this idea. These nebulae are more than just rare sights. They are unique laboratories because every star in a globular cluster was born from the same primordial gas cloud at the same time. They all share the same age and initial chemical composition. They are pristine, uncontaminated by later generations of stars. This gives astronomers a perfectly controlled experiment. When they model how a star of a specific low mass and specific low metallicity, meaning fewer heavy elements, should die, the presence or absence of a planetary nebula in a cluster like M15 or M22 is the ultimate test. It either validates or forces a rewrite of our most fundamental stellar evolution timelines. These ancient clusters, therefore, act as cosmic clocks. The rare, glowing planetary nebulae within them are the final, ticking seconds on the lives of the slowest stars in the universe. Their brief fluorescence a confirmation that even after 12 billion years, a star's final act can still illuminate the darkness. The final, overarching mystery is not about a single strange feature, but the very essence of the nebula itself. After 50 discoveries, from hidden binary stars and magnetic lattices to chemical factories and cosmic wobbles, we are left with a profound and humbling question. Given everything we know, a star's precise mass, its rotation speed, the presence and orbit of a companion, can we predict the exact shape of the planetary nebula it will create? The answer, for now, is a resounding no. Each nebula is a unique masterpiece, a fingerprint. The reason lies in the staggering complexity of the physics involved. This is not a simple chain of cause and effect. It is a turbulent, chaotic symphony where every instrument influences every other. Hydrodynamics, the flow of gas, crashes into the sculpting force of radiation pressure. That radiation is channeled and focused by invisible magnetic fields, which themselves are twisted by the star's spin. All of this unfolds within the relentless, shaping grip of gravity, both from the star itself and from any hidden companion. These forces do not take turns. They interact simultaneously in feedback loops and non-linear dances that our most powerful supercomputer simulations can only approximate. A tiny difference in the initial spin axis, a slight variation in the strength of a magnetic field, or a minute change in the orbital period of a binary companion can steer the entire cataclysm toward a butterfly, an hourglass, or a tangled spiral. So when we look at the cat's eyes nested rings or the butterfly's vast wings, we are not looking at a predetermined outcome. We are witnessing the singular result of a billion variables locked in a violent, beautiful struggle. Each nebula is a final, luminous signature, a one-of-a-kind autograph written by a star at the moment of its death. And that may be the greatest wonder of all, that in a universe governed by immutable laws, the final act of a star's life can still produce something so utterly, breathtakingly unique. So the journey ends not with a single answer, but with a transformed vision. Planetary nebulae are no longer simple bubbles or serene farewells. They have revealed themselves to be cosmic Rosetta Stones, intricate texts written in light, chemistry, and motion that decode the final, chaotic chapters of stellar life. We began with a naming error and ended in a universe of profound complexity, where asymmetry is the rule, not the exception. We found hidden binary partners performing gravitational dances, powerful magnetic fields sculpting from within, and violent jets carving delicate shapes. We discovered these objects are chemical factories, forging and scattering the very elements of life, from carbon cages to complex organic dust into the galactic void. And we learned their breathtaking beauty is a fleeting illusion, a brilliant flash of transience in the vast, dark timeline of the cosmos. Each of these 50 strange discoveries peels back a layer, showing us that a star's death is a dynamic, multifaceted event, a collaboration between a star's fiery heart and the silent architecture of the galaxy itself. This knowledge now turns our gaze closer to home. Our own sun, in roughly 5 billion years, will embark on this very journey. It will swell, shed its outer layers, and for a brief, glorious span, light up its own planetary nebula in our solar system's sky. What shape will it take without a binary companion, perhaps a serene sphere? But if a hidden gravitational dance or a magnetic whisper guides it, our sun too could paint a butterfly or an hourglass upon the heavens, a final, radiant signature for any distant observers to decode. The study of these cosmic shrouds is ultimately a study of our own origins and our distant future. They remind us that we are made of stardust delivered by events just like these, and that even the end of a star is not an end but a transformation, a recycling of cosmic ingredients for the next great story. Which of these cosmic mysteries fascinates you the most? Is it the hidden binary sculptors, the chemical factories forging lives building blocks, or the haunting, transient beauty of these stellar ghosts? Let us know in the comments below, and don't forget to subscribe for more journeys